All right. Welcome back, everyone. So for the second talk, very happy to have Ankur Moitra, who's an Norbert Wiener professor of mathematics at MIT. I'm not going to do a very long introduction because I'm looking through the room. I think most of you have seen at least one talk by him in the past few weeks. All I'm going to say is at least one of the kind of goals of this program is to gain new kind of conceptual insights, come up with new kind of frameworks and abstractions, as well as kind of draw connections to things we do understand, analogize to things we do understand. And reading Ankur's papers is pretty much a masterclass on this. He's going to be around for the year, so talk to him. I'm pretty sure that whatever you're working on, he'll have something insightful to say. Ankur, take it away.
All right. Thanks for covering, everyone. You guys should be sick of me by now. I think this is my third talk in 3 weeks. So I'm going to do a board talk to mix it up. And that's because the thing I'm going to tell you about is really just a collection of stories. And the proof is so simple that I wrote it up here in advance. It's covered. This will be the proof. OK? I haven't told you of what. But I want to tell you like a very simple idea that took me way too long to realize. That this is even an interesting question. And it's going to fit under this general umbrella of, a lot of times in life, we as theorists, we think about very simplified models for how our data is generated because, we feel like the real world is messier than that. And, sometimes it turns out that maybe these real world models that have all these dependencies baked into them, there's a sense in which these dependencies can actually help us get around computational obstructions. So that'll be my goal today. But first, I want to tell you 2 stories that are going to come together. So I'm really just going to give you a review of 2 threads of work that I really like. Let me tell you a little something, a survey about learning graphical models. So in fact, let me not suppose anyone knows what a graphical model is here. And let me just define them for you. So first, from an abstract standpoint, the important thing about graphical models is that they're a rich way of defining high-dimensional distributions. If I have a distribution over some exponentially large set, in high dimensions, I don't want to sit there and write down what its probability density function is. That would be hopeless. Instead, I want to write down what its PDF is in some sort of concise, simplified way, but still a way that allows me to specify important things like what are its conditional dependencies. So that's exactly what graphical models are. Let me give you some examples of them in action, things we'll come back to. So one very popular model is called the Ising model. So this is just a distribution, which is on plus minus 1 to the n. And in particular, the way that you specify it is that you have some collection of variables, capital X1 through Xn. And if you give me some sort of signature little x, which is just a collection of plus 1s and minus 1s, I want to know the probability that these random variables take on this assignment. Well, that's going to be equal to some exponential of some energy function, x transpose jx plus h transpose x, all over a partition function. So let's walk through this and understand what this means. So this term right here is called the partition function. And all it is it's the normalizing constant so that this is a distribution. So in particular, it's the sum over all possible little x's of this quantity in the numerator. I divide through just so that everything sums to 1. Now, the important things for our purposes are things like what happens upstairs. So this matrix right here is usually called the interaction matrix. It just describes, for each pair of random variables, how much do they want to be the same or different from each other. And that'll be encoded by, for example, the sign in the corresponding entry. And then the magnitude will tell you, how strong that relationship is. And, finally, we have this vector of external fields, which just tell us, if I look at one variable and just, focus on it and ignore everything else that's happening, how much is it predisposed to be plus 1 versus minus 1? So this is an example of, a graphical model, right? I'm specifying a distribution over 2 to the n things, but I'm doing so in a concise way because I'm assuming that the distribution has this form. And it turns out that when I assume that the distribution has this form, I can read off a lot of powerful conditional independence properties. So we'll get to that in a minute. But I also wanted to mention that there are generalizations. And these generalizations will be very important for our purposes. You can have generalizations to larger alphabets. Maybe you want to talk about random variables which don't just take on one of two values, but maybe they take on one of k values, and you can think about something which is called a Potts model in that way. Now, for every pair of random variables, for every pair of what their assignments are to these k possibilities, you might have some contribution to the energy function as a result. But what I'll really be interested in is generalizations to what are called higher order interactions. And these are usually called Markov random fields. This is really where I want to get to. And one simple way to define it is that I still talk about my distribution, the probability that capital X takes on the value little x, now is proportional up to the normalizing constant to some exponential. But the key thing is that now, instead of looking at a degree 2 polynomial in this little x variable, I could look at a potentially higher degree polynomial instead. So, just to fix some notation, throughout this talk, I'm going to think about this as being degree at most k. So I could either think about pairwise interactions for my graphical model, or I could think about k-wise interactions. And there's a sense in which, when you go from here to here, you really start to think about and abstract them differently. Because the right way to reason about these combinatorially is as a graph in terms of, what pairs of variables interact. But now your interactions are happening over k tuples, so you naturally think about this as a hypergraph instead, where the size of the edges is up to size k. Okay, so in fact, it's often helpful to look at the graph structure when you talk about graphical models. So we can define an associated graph structure to each of these models. For example, I could have a graph G whose variables are exactly these random variables, the xi's, and I have an edge set which is just telling me which pairs of random variables xi and xj have the property that they have a non-zero interaction. And just for simplicity, you can always just assume that this matrix here is symmetric. So this really is an undirected graph. So the important thing is really the Markov property, which tells us, how separators in the graph relate to conditional independences. So in particular, if you give me two random variables xi and xj, they will be not independent, but conditionally independent if you further tell me what the spins are in some set U. They'll be independent if all paths in your graph G from I to j go through this set U. So these are the key properties. So any questions about what a graphical model is? Makes sense? Probably review for most everyone, but I'm still going to review it, even if you tell me you all know what it is. So let me get to the first main question for one of the two stories I want to tell you. And these are the two stories that are going to come together. So a very natural question in the context of learning is just, can you learn? Can we learn a graphical model, maybe with pairwise interactions or maybe even with higher order interactions from random samples? So this is your belief, is somehow that you have some underlying data and that maybe it has dependencies, but the dependencies are described in terms of this interaction structure. And the question is, if someone is generating data for you from this kind of model, can I learn what all these terms are that govern the types of interactions between the random variables? Given samples, can I learn J and can I learn H? Okay, and I'll punt on the partition function because that's actually a very, very different problem. But that's the basic question, is can you learn J so that I learn the underlying graphical structure? And there's a ton of history on this, as you would expect. In fact, let me just look at the history in the pairwise case. So the oldest work on this dates back, many decades. It's the work of Chow and Liu from 68. And what they did was they showed that the answer is yes for trees. So in particular, if you give me some graphical model, which the associated underlying graph has a tree structure, but I don't know the tree structure, what they did was they gave a polynomial time algorithm to learn the underlying tree structure. Now, there are a lot of caveats that come with this. If I wanted to state the results precisely, I would have to do things like I'd have to have an assumption that when I have the non-zero entries in J, they better be noticeably non-zero, otherwise there's no help that I can decide what's zero and non-zero. So really what happens is that if you have the right lower bounds on the strength of the non-zero interactions, then you can get an algorithm that takes poly running time and sample complexity that can provably learn the underlying tree structure. Yeah.
Is the goal to learn J, or is the goal to learn some distribution that's close in some sense to the induced distribution?
Those are great questions. So it turns out that those are actually pretty different goals. So the types of goals we could think about, in fact, there's a third one. So one is structure learning, which is I just want to learn the zero non-zero pattern for the entries of J. It turns out that in many cases, once you learn the underlying structure, you can actually learn the parameters like the J and the H's. Now, it turns out in some cases that you can't hope to actually learn those parameters, but there's a sense in which you could learn another distribution or a way to generate things that act as if they were. So that last question is a very subtle one, which isn't that related to this talk, so I'm going to skip that, but we can chat about it offline if you're interested.
So in this talk, you're trying to learn the actual parameters.
That's right. In this talk, I'm trying to learn the actual parameters, and I could either focus on structure or parameter learning, but both are really intertwined goals. Great. All right, any other questions? Yeah.
Sample here is an assignment of each of the n variables, plus 1 minus 1. Then you do it again.
That's right. That's right. Exactly. Okay. Yes?
The model that you propose there, the generalization with K, can be seen as also as a generalization of a Gaussian graphical model, for instance?
So, no. Because, I don't want to get too far into this, but computing the partition function will be insanely hard for these types of things. Really, maybe you could squint at this and say it's some kind of generalization of a Gaussian, but the trouble is that really the Gaussian always has this property that I can compute the normalizing constant. And that's going to go out the window here. Keep in mind that this sum, this isn't an integral over all possible choices of x. It's only an integral, it's only a discrete sum over these finite sets right here. But very good question. Okay. All right. So then, there's a lot of beautiful work afterwards. There's a result of Karger and Cerebro. It's actually in a slightly different model, I believe. But in any case, what they did was they showed algorithms for bounded tree width. I won't define what that is, but it's a very nice generalization. And then really one of my favorite works in this, we all have these papers that someone else wrote that we just really loved and wish we wrote them. For me, this is certainly one of them. There's this beautiful paper of Guy Bressler, where what he showed was that he gave a polytime algorithm for bounded degree graphs. So to be more precise, is that what he gave was an algorithm that runs in time f of d times polyon n. The sample complexity is even better than that. And here d is an upper bound on the degree of your graph. And there's also some suppressed dependence on the interaction strengths, lower bounds for the non-zero terms, upper bounds for all the terms. But one of the important things here was that this was actually a very bad dependence because it was doubly exponential. Now, I'll get into some intuition later about why this result is so surprising, but it's a super cool result if you've never seen it before. But this was improved in a sequence of follow-up works, one by Voufray et al. From 16, and one super nice paper by Clivens and Mecca. And what they did, among other things, was that they improved this f of d to singly exponential, and it turns out that that's actually sharp from an information theoretic standpoint. So that's really neat. And in fact, maybe one other comment I want to make is that there are even easier algorithms we know now. Bressler's algorithm was based on some very interesting information theoretic properties of graphical models. But it turns out that really the right way to think about these things is really through logistic regression, but with some type of L1 regularization. So really what I'm going to care about, though, is what happens for higher order Markov random fields. So this was all in the pairwise case. Like if I had an underlying Ising model, it turns out that many of these results can even be generalized to Potts models, where you have random variables that take on more than just 2 random values. But really things become a lot more hairy when you talk about higher order interactions. So let me tell you the end of the story at least. What about higher order interactions? So here it turns out, this is also in the Clivens and Mecca paper. And I guess we proved this too. The point is that there's an n to the theta of k time algorithm for the k order case. So here I'm even suppressing the dependence on the max degree. Let's forget about that. I won't be that interested in this talk. Think about the max degree just showing up somewhere in the front as some very large hidden constant. But what's really going on is that we had this very nice polynomial time algorithm in the case where we had pairwise interactions. And then all of a sudden, in order to think about k-wise interactions, we incurred this incredibly steep price where the k now happens upstairs in the exponent of the n term, right? And in fact, maybe what's even worse about this is that, unfortunately, this is tight. So a folklore fact is that assuming something called the k-sparse parity with noise problem is n to the omega k hard. It's hard to beat that running time, which is a standard assumption in the area. No one's been able to break it in many decades. Then it implies that n to the omega k time is needed for order k Markov random fields. So this is story 1. Yeah?
Something about the statistical sample complexity.
Yeah, so the sample complexity would not depend anywhere that badly on k, because the sample complexity would not have the k in the exponent of n at all. So that's really the issue, is that all of a sudden we have this gigantic computational versus statistical trade-off driven by the k-sparse parity with noise problem. Yeah?
I wanted to ask that because if I'm being naive and just counting the number of degree of freedom and free parameters, it seems like the number of free parameters is n to the k node.
Well, so here, you get a ton of information when you actually have a sample from the model. And, really you're working in a bounded degree case. So, if you could do something like you could guess the neighborhood around some node, you could do things like try to check whether things are actually independent. So I'm not going to go that far into the information theoretic thing, but suffices to say that the types of examples that you derive from sparse parity with noise just have this property that they have way better sample complexity. But that's a very good point. Okay, this is story 1. Okay, so now let's take an intermission. Let me tell you about story number 2, and then let's see how these stories connect to each other. So the second part of the story is related to another neat line of work, not as long as this first line that I told you about, but it's about learning from Glauber dynamics. So I have to tell you what exactly Glauber dynamics are and what it means to learn from them. But let's start off with the motivating question that drives this work, which is, where do the samples actually come from. So in this first story that I gave you, I punted on it. I said, graphical models are a natural generative model for the world. Someone else is generating them for me, and if they're giving me these samples, I want to learn what the underlying graphical structure is. But, who is generating those samples and how? It turns out that there's a computational wrinkle that should actually give you pause about, whether there's a reasonable answer to this question or not. So the main issue is really a property that's called correlation decay. So I'm trying to review, a huge line of work, so I'm gonna have to do some of these things informally. I apologize. But let me define what correlation decay is. So let's consider a family of distributions, which is parameterized by some sort of temperature. It naturally fits into these kinds of models we're interested in. So let's say we have what's called a Gibbs distribution. So we have some energy function h of x. That assigns to a given configuration of spins or choices for the random variables some sort of energy about how much it's compatible with the constraints in our system. But then we toss in this extra parameter beta in here, and our actual distribution is now just proportional to this. So the probability of x being equal to little x is proportional to this e to the minus beta h of x. And h is called the Hamiltonian, but really what I care about here is this parameter beta that's called the inverse temperature. Because intuitively what's going on is, when I take a spin system and I send the temperature to infinity, what's going to happen is I'm really sending beta to 0. And then all of a sudden, nothing is happening upstairs. I'm just looking at the uniform distribution over my domain because my system is so hot that it doesn't matter whether pairs of atoms are really the same magnetization or not. I prefer entropy over satisfying the constraints of my system. But now, as beta becomes larger and larger, which corresponds to cooling the system, all of a sudden, I care a lot more about, how much the system is in agreement with itself, right? I care more about, what types of terms minimize this h of x term so that they show up often in my corresponding samples. So it turns out that there's this very interesting physical picture that happens that's called correlation decay. And there's a whole study of phase transitions in these types of systems. And there are many different notions of phase transitions, but let me tell you one simple example of a phase transition, which is imagine I take large enough beta. And I can draw this picture where maybe I have some site x, and then I look out at some distance in the corresponding graph, and then I look at some boundary at that distance. These are all different sites in my corresponding graph. Now imagine what I do is I pin the boundary somehow. So I fix all the things on the boundary to either being +1 or -1, however I want to do it. And then what I can ask is how much does that pinning affect the marginal distribution at x? So once you tell me that that boundary configuration is the way it is, how much does that change your belief on the marginal distribution of what the spin on the site x ought to be? So it turns out that for large enough beta, the point is that the marginal distribution, the marginal on x for any pinning, is about the same. Or, to be slightly more quantitative, what you hope is that, for some large enough beta, in the limit as delta goes to infinity, that the effect of, the choice of the boundary is going to 0. It's vanishing. So it's little o of 1. Yeah?
What does pinning mean?
It just means conditioning. So I condition on all of the nodes in the boundary, y1, y2, and so on, being equal to some spins, like either +1 or -1. And the point is that in principle, different choices of how to set the boundary can lead to different marginals.
This is a graph about coordinates of the x vector.
That's right. Exactly. That's right. That's right, exactly. So this would be if I take my underlying graph that describes the dependencies among the random variables, I fix one node, and then I look out at some distance delta in graphical distance from it, and I tell you what the distribution is realized on the boundary. The question is, for what values of the inverse temperature is it true that the boundary becomes irrelevant? So intuitively, you know, when I think about beta being 0 and I'm at the infinite temperature case, then, you know, every node becomes independent, so it doesn't care what the boundary is. But there's a precise phase transition in terms of beta that has to do with the degree and the interaction strengths that tells you when the boundary does or does not matter in an asymptotic sense. Yes?
About the same graph as the non-zero J graph.
Absolutely. Yes, exactly. Perfect. Thank you. All right. Any other questions, especially clarifying questions? Okay. All right. So here's a really beautiful theorem. Another awesome theorem in this space, which is that it turns out this is a work of Sly and then, you know, a work of Sly and Son from just shortly after it. And I won't tell you the class of graphical models that it applies to, but it's a very, very rich class. It'll take us too far afield. But in certain important classes of graphical models, sampling from this Gibbs distribution, this distribution that I wrote down here, this is my Gibbs distribution, and it's parametrized by this inverse temperature. Well, what they show is that it's computationally hard at temperatures where there's no correlation decay. So this is one of the beautiful results in approximate counting and sampling because, you know, usually we care about lots of phase transitions, right? You know, we care about structural properties in the underlying distribution. But in this case, what ends up happening is that the structural properties undergo a phase transition at the same exact point where there's a computational phase transition, where the problem goes from being computationally easy at high temperature, there are efficient algorithms for sampling from the corresponding Gibbs distribution, to becoming computationally hard. So, you know, let me put this in perspective, right? There's a very nice quote that I really love by Kamal Jain. Let me quote him here. So, you know, this was said really in the context of doing things like computing Nash equilibria. So, you know, computing Nash equilibria, people believe that Nash equilibria is a good model for how economies work, or maybe they less believe that these days. But, you know, of course, we have very famous results that show hardness for computing a Nash equilibria. And he had this very nice quote that I love, which is that if my laptop can't find it, namely the equilibrium, then neither can the market. So maybe computational lower bounds teach us something very important about what we believe are natural solution concepts in the world around us. You believe that it's Nash equilibrium. Well, how are you going to explain, you know, how are you going to justify that my laptop can't find it and you think that the market is finding the equilibrium? Maybe that's not a good idea. So let me offer a twist on Kamal Jain's aphorism, right? Maybe if my laptop can't find it, namely like sampling from the Gibbs distribution, then maybe it's not a defensible generative model. Maybe it's not actually reasonable that my samples come from a Gibbs distribution if my laptop can't find it. All right, so maybe I should change it to my quantum laptop, but let's not go there. All right. So then I have to tell you about one more piece, which is, you know, I told you I wanted to think about learning from Glauber dynamics. So what exactly are the Glauber dynamics? And then we can start to see how these stories come together. So, what Glauber dynamics is is it's just a Markov chain on an exponentially large state space that eventually mixes to Gibbs. And the way that this works, see, if you think about the natural setting we're in here, we really have an exponentially large state space because for each node I have to decide whether it's -1 or +1. And maybe what's going on is that let's say I have some sort of corresponding graph that looks like this, and maybe I'll color in the nodes that are +1 and leave open the nodes that are -1. That's my current state of my system. And then what I'm going to do is I'm going to choose one of the nodes in the graph, and I'm going to forget about its spin. But then I'm going to fill in its spin with the correct marginal probability. So there's some chance that it becomes -1 instead, right? And that's my state S0. And there's some chance that when I fill in the spin, I go back to where I started from, and I'm still in the state S1. So the important thing is that, for these types of graphical models, even though it's hard for me to do something like compute the partition function, because that's really a sum over all possible configurations, this right here, computing the ratio of their probabilities, that doesn't actually depend on Z, and all I have to do is compute two different, things that go upstairs, one for each one of them. So once I compute these two things, I know what's the right marginal, probability that I should be in S0 versus S1 if you tell me I must be in one of those two states. So the important thing is that you just take these transitions with appropriate probabilities, which can all be figured out from your model. And then if you prove things correctly in terms of detailed balance, you'll eventually converge to the correct Gibbs distribution. But the question is just how long will it take you? Because this is an exponentially large state space, right? I don't know. Yeah. I don't know. I'm not sure I would be able to answer the historical aspects of where the name came from right now, but we can figure it out. Okay, so, all right. So now, really the second story that I want to tell you, it's a very natural question, right? Which is, even when Glauber is slow. And by that I mean really slow, because it maybe takes exponential time to mix, right? What you could ask is, can we still learn from it? Because maybe it's a way to answer this kind of challenge, right? So instead of assuming that my samples actually come from the mixed Glauber dynamics, because that's too much, it's computationally hard, what if instead, I assume that my samples are just generated from some trajectory over Glauber? So these types of trajectories are very natural in a lot of contexts. People use them to model all kinds of dynamics, like on social networks. Things like, whether you have an iPhone or a Pixel, and then maybe there's some sort of positive or negative association with your neighbors in the social network. But then you use things like Glauber as a way to model, how a technology spreads through the social network. You can use it as a way to model, the actual dynamics of a physical system. But in any case, the point is that, maybe that's the thing we really care about, is the natural underlying dynamics, whether or not they reach equilibrium, this thermalized state or not. So there's some very nice work here. So there's a very nice work of, Bressler et al. From 18, where what they do is they show that, there is an algorithm for Ising models, but in particular, it solves the slightly weaker problem that's called structure learning, where it just learns the zero non-zero pattern of the underlying graph. So what's going on here is we already had Bressler's algorithm for learning bounded degree Ising models with pairwise interactions from samples from the Gibbs distribution. But now instead, if you give me a trajectory that has polynomial length but comes from the Glauber dynamics, that turns out to still be enough in order to learn those same family of Ising models, just with the caveat that it's structure learning and not parameter learning. But thankfully, even this problem was solved, recently in a very nice work by Jason Gaitonde and Elchanan Mossel, just from this past stock. So what they do is they can also handle parameter learning. So these are the two stories I wanted to tell you, and now let's try and have them come together. So let me get to my main question. And then it turns out that the proof is really quite easy once we have all of the setup and background in place. So what's my main question? Is, does Glauber, does having temporal dependencies within your sequence of observations, because it's evolving from a trajectory, does Glauber make learning easier? So this is a different question than what was being answered here, right? Which was really about whether Glauber is good enough. I don't have samples from my Gibbs distribution, but is Glauber good enough to act as a surrogate? And all these things, you're doing what you could already do from Gibbs samples, but for something that's maybe a more natural generative process. But maybe we could be more optimistic. Maybe these temporal dependencies that happen over the course of the trajectory from the fact that you're not actually mixed are actually things that we can harness to our advantage, because they also teach us something very important about the underlying dependency structure, right? So that's what we did. So the answer is yes, for higher order and still bounded degree Markov random fields. Now the important thing is that we're going to be able to get away with this with just n squared log n time and actually n log n length trajectories from Glauber, from an arbitrary starting configuration. The constants hide things that depend on the max degree and the order of the interactions. But the important thing is that there's no k upstairs. So, a priori, we believe that these higher order interactions are very important. They show up in all kinds of natural systems. But then it turns out that actually these temporal dependencies of Glauber are exactly the missing ingredient to get around the sparse parity with noise barrier. So any questions about what I'm promising you should be true? Does it make sense? Yeah? They are. So they're exponential in the degree, and part of the reason why the exponential in degree is needed is because if you look at a single site, then there could be so much weight preferring one configuration or the other that unless you have exponential in the degree many samples, you would actually never see it being -1, for example. So it's more that you just wouldn't get any updates from Glauber, and the trajectory would be sort of trivial. Yeah?
So the difference between the 1 and 2 and the theorem that you just quoted is 1 and 2 only are for graphical?
Ising, yeah, pairwise, exactly. Exactly. Perfect. Was there one more question? Yeah.
So for second order, like the graph, I understand what D is. But for higher order, what is the degree precisely?
Well, so here this would be like you look at the worst case over nodes of how many hyperedges they belong to. But thanks. Yeah. I'm still going to suppress all the parameters though. All right. Yeah.
What do you mean by time and length?
Right. So someone is going to give me some length of the Glauber dynamics trajectory. I might run in more time than the length of the trajectory in order to actually figure out what the underlying graph structure is. That's why the running time is quadratic as opposed to, nearly linear. But in principle, my algorithm can, do things like look at pairs of, updates over the Glauber dynamics, and that's kind of what it'll do. Yeah. Okay. So I have, I think I started 10 minutes late. Okay.
So is it a single trajectory of that length, or you see many trajectories?
Single trajectory, yeah. Okay, so I think I can prove this. In fact, I lied to you. I told you there was only going to be 2 stories, but there'll be one more story. So first, let me tell you about the Bressler et al. Approach. It's very super natural, very intuitive. And then I want to tell you a bit of a digression that's going to give us the proof for higher order. It'll give us the intuition for what's going on. So let's do, the proof sketch of this result of Bressler, Gamarnik, and Shah that I told you about. And the main question here, since we're just doing structure learning, is can we decide if ij is an edge or not from the Glauber dynamics? And here's what the strategy is. So what we're going to do is we're going to wait for a signature. And this signature will be described as iji. And what I mean by this is maybe I want 3 contiguous updates. The first one tries to update site I. So it hides whatever used to be the spin for site I, and then it resamples that spin. And then it goes to j, and it tries to update that, and it actually succeeds in updating. And then it goes to I, and then tries to update that, and it might or might not succeed. Now, the important thing is what's going on here is that what this allows us to do is it allows us to estimate quantities like p minus p prime, where what p is here is the probability that xi is equal to +1, conditioned, let's say on xj equal -1 and everything else. And similarly for p prime, except for the fact that now you're conditioning on xj equals +1, because as you've passed over this update, you've updated whether xj is +1 or -1. So the important thing is that now, I'm getting a sample from this distribution that tells me, in expectation what p is, in expectation what p prime is. So what you can do is you can then take, some sort of empirical average. This actually turns out to be a bit more subtle. See, the big issue with this is that the empirical average doesn't quite work in order to estimate these quantities, because there's another hidden dependence that you might not see, which is that, once you condition on the fact that j has updated, that actually changes the probability that, I is actually updated. Turns out there's a fix for that, and this was actually overlooked in the original paper. But there's some variant of an empirical average. And then ultimately what you do is you decide, ij is an edge if and only if your aggregate statistic that comes from some sort of empirical average is far enough from 0. So the intuition here is that when I have pairwise interactions, there's a unique way that j is going to affect I. If there's a positive interaction, then whenever I have j being +1, then it actually makes I being +1 more likely to happen. You're more likely to accept that move of the Glauber dynamics than if j were -1. So in fact, the point is that the influence of j on I happens in a consistent way across all of these different instances and locations where they get updated in Glauber. Yeah.
When there's no change made in the system,
yeah,
between steps, do we know which vertex a change was considered for?
Yes, we do. So that's a very important thing here. And actually, one of the main open questions is to get around that assumption. So here, what we're doing is we're actually assuming that we see the trajectory of Glauber. It could be possible that you only need to see the updates of when the actual spins were updated, but I don't know how to do that yet. But very good question. All right, any other questions? All right. So let's just think about, I'm just going to I'll just keep the sketch, okay? I'm not going to go into too much more detail than that, but I want to give you one more connection to give you a piece of intuition for this. And, why doesn't this work for higher order dependencies? Let's draw a picture. Maybe I have I and j, and then they participate in some hyperedge with k. And then maybe they also participate in some other hyperedge with k prime. So now the issue, right, is that j might affect I, but he actually might do it through two different pathways. He might affect it based on this ijk prime edge and this ijk edge. So the issue is really that it doesn't affect the spin of I in a consistent way. In fact, sometimes it might have a net positive effect, that it's more likely to have the same spin. Other times it's more likely to have a net negative effect. And what happens as you average over the trajectory where the rest of the system is changing, why can't these things almost cancel out or become very close to zero? So that's really the issue. Another more precise way to think about it is that one way you can measure the effect of conditioning is really through partial derivatives. It turns out that what's going on here is you're really taking partial derivatives based on I and j of your energy matrix. But when this is degree 2, when you take two partial derivatives, you're going to get down to a constant term, and that has one fixed sign in terms of the influence. Whereas here, when I differentiate twice, all I've done is reduce the degree, but I still have a general polynomial that as I average over samples from even Gibbs or something else, who knows what it does? How can I set my actual threshold? So let me tell you one last story, which will help all these things tie together. And this is a very natural problem in statistics, which is called the population of means problem. It's a beautiful problem. And here the idea is that suppose we have some parameter theta, which is the bias of our coin, that comes from a distribution mu. But then what happens is that we don't see theta, and instead we get samples x1, x2, all the way up to xk, which are sampled IID from a Bernoulli distribution with parameter theta. We get that batch of samples, we see what the configuration is, and then we sample a new coin. So this is very useful in things like testing, because the way to think about it is that maybe theta, this distribution mu represents a population of students. They each have some different intrinsic ability theta, which is sampled from some distribution mu. And then you have some exam questions. They either get them right or don't, but they have some probability of getting them right based on their underlying ability on that test. Now, the interesting thing is that I can't actually estimate the ability of each individual student all that well. Think about k being 2. I give you a test with just two questions on it. I definitely can't tell what your intrinsic ability is. But in fact, I can learn a lot more about mu than what I can learn about the individual students. This is usually what's called a shrinkage estimator in statistics. For example, what you can do is, even though you can't estimate the individual thetas that arise for the students, you can estimate things like mu's first k moments. Right? And in particular, this allows you to do things like can decide. You can decide if mu is a point mass. Maybe it's a point mass on a half, and all students have the same ability because that ability is 0 and they're randomly guessing, right? That would be something that's uniquely determined based on the first two moments, because you tell me the mean, it's a half, you tell me the variance, it's 0. And then even though for each individual student, if I wanted to find the best estimate of their theta, I would use the empirical average. It turns out that I can actually get a much better estimate of the overall distribution of mu, based on what are called shrinkage estimators. So now, really the point is that when I have this Glauber dynamics, right, what's going to happen is I can tell you what our proof is. We're just going to wait for a different signature. II. So now the important thing is, ignoring that complexity I told you about the hidden dependence that can be handled. If I think about two worlds, I've fixed the rest of what happens in my universe on all the other sites, but now I vary whether the spin of j is +1 or -1. What's going on is that this type of quantity right here allows me not to estimate p, but p squared, because I get two samples from the corresponding conditional distribution, which tells me whether or not Glauber accepts the updates. And then I get two samples from p prime, right? And the fact that I have two samples is the thing that allows me not just to get p and p prime, but to get their second order moments, which is p squared and p prime squared. So the entire point is that now, what is the strategy going to be? We're going to try and empirically estimate p minus p prime squared. And that's it. Because the point is really that as long as you have some bounds on the strengths of these interactions, then what you can show is that when I condition on the entire rest of the system, you should expect that usually j has some effect on I, and that it actually affects, p versus p prime. And now my statistic is really whether this quantity, which I can get from estimating events like this, is that significantly far enough away from 0. So I can't go too much more into the details, but I just wanted to point out that really this is the kind of thing where it comes from, is that once you have not one sample, so if I had one sample, there would be no hope for estimating anything about mu. I couldn't tell whether it was uniform in the interval 0, 1, or a point mass on a half, or 2 point masses at the endpoints. But once I get samples of size 2, then what I can do is I can actually get the first two moments and decide whether something is a point mass. And what I really care about here is that once I fix the rest of the system, I care about, as I vary j, is that probability of I actually a fixed thing independently of j or not? You can use things like anti-concentration of low-degree polynomials to show that as long as they belong to some non-zero term, there's a good chance that when I restrict randomly the rest of my system, they still have some non-zero interaction. And then just getting second-order moments, which just come from the signature II, is enough to estimate this quantity, to learn the structure, and then to do parameter learning. So that's probably all of the proof that I could reasonably get across in a board lecture, but happy to take more questions or answer more questions offline, but thanks for your attention.
So could you help me understand the following? So in Glauber's net dynamics, it's one node at a time, right?
It's what?
It's like chooses one node at a time randomly.
Yeah.
And the length of the trajectories you get, it was like n log n.
Yeah.
So how isn't it short enough to see even one of those?
Right. So really, the other parts of the proof that I didn't tell you about is that I don't actually have to look for this as a contiguous signature. So long as they happen close enough to each other, I will get lucky enough times that there's no updates to the common neighbors of I and j, and then I can get by with things that are, n log n for the trajectory length, but I basically have to do some brute force search over I and j. So that's just sort of a further refinement. There's a bunch more tricks that go into the paper, but I think when we were discussing this question, Jason, Elchanan, and I, maybe one afternoon, Jason said, let's look at II. And those 5 letters were the proof. The rest of it is just details. Yeah.
So going back to the motivation about real-world sequences,
Yeah.
A natural model is like someone ran Glauber dynamics, but you got a subsample from this because someone went and collected data from this.
Yeah.
So do these techniques work at least philosophically for sequences of that form?
Maybe, but I still really like the question Russell asked first, which was if you only see the actual updates, can you still do these types of processes? So I think there's a whole, host of interesting directions you can go in, which is what do you actually need to observe? But my point is just that in cases where it's not reasonable to expect that the samples actually come from Gibbs, The fact that you can actually model the process by which your data comes from, be it you see every update in Glauber, or be it you only see the things that actually change the values, those actually leak a tremendous amount of information about the underlying graph structure. Those are the things that you wish you had, because really the trouble with Gibbs is that in order to decide whether I and j are in the same hyperedge, I would a priori need to know the rest of the hyperedge, to condition on. But here, the fact that these two samples are so close to each other and have so much to do with each other is actually a strength and not a weakness. So maybe my point is more just that learning from dependent data can get you around limitations from learning from the simplest possible independent sequence of data. But, really this is just an invitation for you guys to solve the other questions that show up here. Yeah.
So for the case where you don't see the index levels, like when it just doesn't change, the issue with simulating an index is that if you condition on there being no transition, then you don't know that it's happening.
Yeah. So I will tell you one more story, which is that, so I learned about this population of means actually from a really nice talk that Greg Valiant gave. And it turns out that, one of the scientific open questions is, in biology, is whether the gender of your kid has to do with the date of conception. So people have all kinds of theories on, how, depending on whether it's sooner or further from, ovulation, whether date of conception is further away from ovulation, whether that affects the gender. But there's really no way to test these kinds of things naturally, right? Because you don't know exactly the timing of events. But one of the things he did was he thought about whether you could do this for populations of dogs. Because dogs have very large batches and they all had the same date of conception relative to ovulation. So you can ask the question, if my batches are really just litters of puppies, can I use the statistics I have to decide whether mu is a point mass on a half? There's no influence of, distance of time from ovulation or not. Unfortunately, what he told me was that in the US, there are too many privacy laws about the genders of your dog litters. So he managed to get some data, I think, from Sweden. But unfortunately, it wasn't enough to reject the hypothesis that it's just 50-50 always. And that's probably the right answer. But for those of you who are basketball fans, I think they also applied this to basketball data. And you can ask whether, some three-point shooters are more streaky than others. Each batch is like the three-pointers they shot. And, interestingly enough, who was the L infinity of the most consistent three-point shooter? Steph Curry, right? So it turns out that any given night, he's about a 42% three-point shooter. Let me ask a tougher question. Who's the least consistent three-point shooter?
Shaq.
No, that's just a zero. Danny Green. So Danny Green has this nickname in the NBA called Icy Hot because you never know what he's going to be. And actually, if you estimate their associated mu, for Steph, you kind of get something that's very much a point mass, around like 42, 43%. And for Danny Green, you get, not a point mass. So anyways, these are fun things to play with, and it's neat that they lead to such a simple proof. But let's stop for lunch, so thanks for your attention.
Oh, I forgot to ask,